Right. So how resonance is going to affect the IR absorption is, again, we have to study it according to the Hooke's law, which states that the wave number is equal to 1 upon 2 pi c into under root of k over mu. So k is the force constant, which is indicative of the bond strength. Nu air is the reduced mass, and this is the wave number, that is nu bar. Okay. So if we just look at a carbonyl compound such as given here, this is a polar bond, the CO bond is polarized. Now this polar bond is actually a double bond having a wave number is 1715. That means it shows a peak in IR spectrum at around 1715 centimeter inverse. When we conjugate it with another double bond, such as shown here in this case, what happens to the frequency of a carbonyl stretch? This decreases actually. And the reason for the decrease is because of the delocalization or the resonance effect, the pi bond actually moved towards the oxygen. And the CO bond, which was earlier a double bond, now has been transferred more towards a single bond character. Okay, so now the conjugated carbonyl compound has more of a single bond character as compared to the double bond character in an unconjugated molecule. So single bond character means the bond strength has slightly decreased. The double bond is more strong as compared to the single bond. So any factor which leads to pushing the double bond towards the single bond will decrease the wave number and the signal at which the spectrum was giving you the absorption of this band. For example, the absorption of unconjugated carbonyl compound was appearing at 1715 centimeter inverse, but after conjugation, because the strength of the bond has decreased, its signal appears at lower value, that is 1680 centimeter inverse. Okay, so this was the effect of resonance or an extended conjugation on the IR frequency of the band. Second effect is inductive effect. Here, inductive effect actually depends on the nature of group that is attached to the bond under study. So if we are studying the carbonyl bond, the electron withdrawing group, if we see, is going to increase the strength of this double bond as shown by the red arrows here, because the X is pulling the electron density towards itself. So the pi bond density is not going to oxygen, but it is coming over to the carbon, leading to strengthening the double bond even at a higher extent. Because the double bond extent is more, that means the bond strength or the K value has increased, which ultimately leads to an increase in the frequency of absorption of this CO bond. Okay. On the other hand, if we have an electron releasing group attached to carbonyl group, this will push the electron towards the carbon, and as a result, the electrons, pi electrons between carbon and oxygen will be pushed towards oxygen. And this gives rise to more of a single bond character in this carbonyl group. So single bond character is more means the bond strength will decrease or the K value will decrease, and the decrease in K value will ultimately decrease the frequency of the absorption. Okay, so these two are the fundamental effects which ultimately gives rise to different positions of the same bond appearing in IR spectrum. So we, in both the cases, we have carbonyl groups, but these carbonyl groups, whether they will be appearing on the higher frequency range or a lower frequency range, will depend on the nature of the substituent present. If it is an electron withdrawing group, the frequency will increase. If it is an electron releasing group, the frequency will decrease. Now let us study the effect of substitution on this carbonyl stretching absorption. We have seen that all aldehyde ketones, carboxylic acid, amides, acid chlorides, anhydrides, as well as esters, they all have the carbonyl group, that is C double bond O structure, and they all absorb in the region of 1650 to 1850. Now, which functional group will absorb at a lower value and which functional group will absorb at a higher value will be dependent on the additional substituent present over this carbonyl group. Okay, so we have a range from 1650 to 1850, and if we take the average of this value, you will be around 1750 or 1740. Let us take the average as 1740 here. So K value of CO bond is on an average absorbing at 1740 centimeter inverse. Any factor which is going to increase the bond strength will make the frequency go towards the higher value, and any factor which decreases the double bond character or increases the single bond character in the molecule will decrease the signal towards the lower frequency values. So let us see in all these functional group, starting from ester. If you see the carbonyl group in the ester molecule, here oxygen is attached. Now oxygen has both the effects. It can have inductive effect. It can also have resonance effect due to the presence of lone pair on this oxygen. But in case of esters, as we have mentioned here, the inductive effect is little bit stronger than resonance, because through inductive effect, this is electron withdrawing in nature, and this electron withdrawing group will ultimately push, or I would say pull, the electron towards itself, making the double bond character stronger. So more double bond character means the strength of the CO bond will increase, and hence the K increases as well as its frequency. Both of them will be increasing. So in ester, the frequency has increased from 1740 to 1745. Moving over to anhydride. See, this oxygen again has inductive effect, but in this case, this inductive effect will be stronger. Why? Because adjacent to this oxygen, we have a positively charged carbonyl carbon. So this carbonyl carbon is delta positive and this oxygen is delta negative. Because of the positive nature of this carbon, this oxygen becomes even more electronegative and pulls the electron towards itself more strongly. So here I would say the anhydride inductive effect is even more important due to the adjacent carbonyl group. And because of the inductive effect, electron withdrawing nature, the bond strength will further increase, K increases, and then frequency also increases. But note that anhydride has two values of the frequencies, one for one carbonyl group and the other one for other carbonyl group. Okay. So there are two carbonyl groups in anhydride. One appears at a lower frequency, other one appears at a higher frequency. Anyone want to ask anything? Is there any question from anybody here? No, okay. So keep your audio on the mute session. Only when you have questions, put it on, okay? Asta has just joined.
Yes, ma'am. Good morning, ma'am.
Good morning. I'll mark your attendance a little later. Fine. Now, continuing our discussion here, moving on to acid chloride. In acid chloride, the inductive effect you all know for halogens is the strongest. So because of the highest inductive effect from the chlorine atom or any halogen atom here, the double bond character of the carbonyl group becomes strongest, and hence the force constant increases to a higher value, and thus the frequency also moves to the highest value, that is between 1800 to 1815 for acid chlorides. Now, moving on to the other side of the average value, that is from this 1740 value to the right hand side, aldehydes. Aldehydes contains the alkyl group, one alkyl group, and you know alkyl groups show positive inductive effect, I plus. So this plus I effect is pushing the electrons towards carbon, and in consequence, this carbon is pushing the electron towards the oxygen. So pushing this electron towards the oxygen is only going to reduce the double bond character and increase the single bond character. So due to this, the bond strength decreases, that is K decreases, and the frequency or correspondingly also decreases. So from 1740, we have moved on to 1725 in case of aldehydes. Okay, we are running out of time. So shall we again join the meeting once more? I'll send you the meeting password. Okay, so I'm just finishing this session now.
Okay, ma'am.
Mansi has also joined. Okay.